Okay, so we've covered how this negative sign is the key to the direction of the induced EMF. And one thing you can, or one way you can think about this is that if the flux is changing, say it's increasing, then the EMF is going to decrease. It's going to be negative. So if this is positive, this will be negative. So one way to say that is that this EMF, this induced EMF, is opposing this rate of change. And similarly, if this rate of change is negative, then the EMF will be positive. So the EMF always opposes the change. Okay, so this is a heuristic way of justifying this, but I'm going to show you now a shortcut where you can use this idea that the EMF opposes the change to figure out the direction of the induced EMF without doing any math. And this rule of thumb is called Lenz's law. Your book actually calls it Lenz's rule. But here's how Lenz's law works. As I move this magnet, the north end of this magnet, towards this coil, I know right away that the current and the EMF is going to be this direction. Okay, so how did I figure that out so quickly without doing any math at all? That's Lenz's law, is the shortcut. Okay, and so to understand the shortcut, forget about the magnet for a second and say that we just have a current going around a coil. Okay, no magnet, just a current going around a coil. We've already talked about how in this situation this is basically an electromagnet. So this current that's going around is turning this thing into a what looks like a bar magnet. And we can use right hand rule number 3, okay, to figure out which end of this electromagnet is north. So as I curl my fingers, imagine I'm holding the cylinder in my hand so that my fingers curl in the direction of the current and my thumb points in the direction of the North Pole. So I've induced, so I want to put north induced and south induced. So by moving this magnet closer, I've turned this solenoid into a magnet with a north and a south end that oppose this incoming magnet, right? This is going to repel the incoming magnet, right? And so this is Lenz's law. Lenz's law is that the rule of thumb is that the current, the EMF, and therefore the current that is induced will be in whatever direction is required in order to oppose this magnet doing whatever it's doing, whether it's getting closer or farther away, right? So it opposes the change. So let's do another example with this time pulling the magnet away. Okay, we already know from my demonstration that it's going to be the opposite direction, but let's see if we can get that with Lenz's law. So the magnet, the north end of this magnet is moving farther away. So this, in order to oppose that change, would want to try to attract this magnet to keep it from moving away. So it would want to induce a south pole on this end and a north pole on this end. And so what direction must the current be going? Well, as usual, right hand rule number 3, I point my thumb in the direction of north, and my fingers are going to curl around in the direction of the current. And so you can see that the current is going this way this time. All right, now I flip the magnet around. So now the south pole is facing the solenoid. Okay, and let's say I move the magnet closer. What is the direction of the induced EMF and therefore the induced current in the solenoid now? So try this yourself. Pause the video and see if you can use Lenz's law to figure out which way the current is going to be going in this solenoid as the south pole of this magnet moves closer. Okay, so if the south end is coming closer, this is going to want to oppose that. All right, so it's going to induce a south pole on this end because south and south repel, right? So it's opposing the fact that this magnet is moving closer, saying, no, I don't want you to get any closer. I'm going to try to push you away. And so the north end must be over here. And so I point my thumb in the direction of the north and my fingers curl around this direction. And then down here, south is going away. So it's going to induce a north pole to try to keep it from going away, try to pull it back. And right hand rule, thumb points with north, my fingers curl around the cylinder like this. Now, I want to emphasize the wording. I'm definitely personifying these things by talking about what they want, okay? So take that with a grain of salt. They don't want anything. But when I said that this one wants to try to attract this magnet to keep it from going away, that doesn't necessarily mean it succeeds, okay? So another way of putting this is, Lenz's law helps us figure out the direction of the induced EMF, okay? But it does not give us the magnitude. The magnitude comes from Faraday's law. So you have to go back to Faraday's law if you want to know the magnitude of the induced EMF. And Lenz's law is a shortcut to figuring out the direction of the induced EMF. Okay, so make sure you keep those uses separate. One gives you the magnitude, the other gives you the direction. And so Faraday's law also gives you the direction. Going back to my previous page again, it gives us a direction because of this minus sign. So you can get the magnitude by taking the absolute value of both sides here, and that will give you the magnitude of the EMF, and that way you're not worrying about this negative sign. And then in order to figure out the direction, instead of dealing with a negative sign, you can use Lenz's law. So in a way, Lenz's law can take the place of the negative sign in Faraday's law. So a common follow-up question is, why does nature do this? And that's equivalent to asking, why is there a negative sign in Faraday's law? Why isn't it a positive sign? And I don't have a short answer to that. But one way to think about it in this case is that nature will act to oppose any changes. Okay? So in that sense, it's very much like inertia. Think about inertia as the resistance to change. This is inertia, but this is electromagnetic inertia. So you can think of this like that Faraday's law, along with Lenz's law, is describing electromagnetic inertia, the nature's tendency to resist change in an electromagnetic sense.